Welcome back to another video. Today is Monday, and I want to emphasize how important the survey for today is. So this survey is actually your evaluation on your teachers, and it is important that you do it because this is how we know if we're doing a good job or not. I want to emphasize how confidential this is as well. So whatever you put, we will have no idea exactly what you will be putting on it. The only thing that we will know is whether or not you complete it. So please be 100% honest. We need real feedback. And so I know that you do this every year. Make sure that you get this done by today, Monday, by 12 p.m. Please, this is an important evaluation of your teachers, so I want to emphasize it once again. Super important that you do it. It's going to be located on either my general channel, and I know that other teachers also post a survey in their general channel, but it will be located in the survey channel in my Teams account. So please do that, or I'm going to start bugging you, and I want to make it clear. It's 100% confidential. We don't know what you will be putting on those surveys, but we do need you to be honest. So with that being said, let's just take it back to the lesson today. And intermolecular attractions is a very important concept, especially if you are thinking about going into the STEM field in college or university. Like, for example, you want to become a doctor or a veterinarian, a dentist, a nurse. Those are STEM field related jobs, and you're going to have to go over organic chemistry. So you're going to take organic chemistry when you're in college or you're in university. Intermolecular attractions is a huge concept in that class, and even so in general chemistry, which you will be definitely taking for sure. So it's better that you get this concept understood right now at the high school level so that you have no difficulties jumping on board to organic chemistry. And I promise it's not a hard concept. It's just a lot of definitions and just it's an okay lesson. But without much further ado, intermolecular attractions, it's the glue to molecules. So we've seen how atoms and other atoms attract each other. That is, like, for example, covalent, ionic, and metallic bonds. Those are a different type of attractions, and that actually leads me to the next slide. And pause this video, make sure that you have the definition of an intramolecular attraction. Keep in mind this big difference of the name. Intra it's a huge difference between inter. Okay? So intramolecular attractions, they're forces that holds the atoms together within a molecule. And you have already seen three types of intramolecular attractions. The first intramolecular attraction listed is the covalent bonding. Remember that a nonmetal that is bonded to another nonmetal, that is a covalent bond. And that's when I share electrons together. That sharing of electrons that forms a bond and that holds these two atoms together. That is an intramolecular attraction. Another type of intramolecular attraction is an ionic bond. And this occurs when I have a metal and a nonmetal. The nonmetal takes away an electron from the metal, and they form a cation and an anion. These ions have different charges, and the positive will be attracted to the negative. This attraction of ions, that is known as my ionic bond, is an intramolecular attractions. And then I know that we've mentioned metallic bonds, and we just don't cover them as in great detail, but a metallic bond is also a type of intramolecular attractions. So make sure that you write this definition down of an intramolecular attraction, and it's what holds atoms together within a molecule. So when I have atoms being held together, they form a molecule. Now that we've defined what an intramolecular attraction, it's time to define what an intermolecular attraction. So I need you to write these bullet points down. Pause this video, make sure that you have this written down in your journal. So an intermolecular attraction, again, remember, huge difference in the name between inter and intra. It's just an attraction between two different molecules. So the biggest difference between an inter and an intra attraction, it's that with an intra, it's between atoms. With inter, it's between molecules. These forces, the intermolecular attraction forces, they're much weaker than the intramolecular forces of attraction. But they're still very important because they determine the physical properties of molecules. With stronger intermolecular attractions, then I need more energy to pull these molecules apart. If I need more energy to pull molecules apart, then that also means I will have a high melting and boiling point, because it requires much more energy to pull away stronger intermolecular forces. This image on the right is also a very good image that you need to write down so that it's, if you're a visual person, you know what an intermolecular attraction, how it looks like. So in this example, I have hydrochloric acid. It occurs between a hydrogen and a chlorine. This molecule is polar. If you don't know where these charges are coming from, then it's a good idea to review the polarity video that I posted last week. But because this molecule is polar, that means I'm going to have a partial positive on the least electronegative atom, and chlorine gets the partial negative charge because it's the most electronegative atom. This partial negative on the chlorine is going to be attracted to the partial positive of another molecule, in this case the hydrogen. This attraction between partial charges is known as my intermolecular attraction. And so this is the glue that holds these types of molecules together. So this slide is super important, so make sure that you have it written down. The difference in this image between an intermolecular attraction, I want you to note that this happens between two molecules, and then intramolecular attraction happens between two atoms. So in order to summarize what an inter and intramolecular forces are, this image perfectly summarizes the entire thing. So we're going to reuse the example of hydrochloric acid, but we need to form intramolecular attractions first. So remember that the intramolecular attraction occurs between two atoms. This hydrogen and this chlorine, they're going to form a polar bond, and this is actually a covalent bond between hydrogen and chlorine. Both are non-metals. And in order to depict this intramolecular attraction, I'm going to use the example of a thread and needle. So I'm going to sew these two atoms together, and this thread and needle is actually pretty strong. If I try to pull this hydrogen and chlorine, it requires so much energy on my part to pull them apart. Now that I have a molecule of hydrochloric acid, when I thread and needle a hydrogen and chlorine together, I want to attach my hydrochloric molecule with another hydrochloric molecule, and a perfect example of an intermolecular force is like Velcro. Velcro, they're important in our lives because they help things stick to each other, but it's not difficult to separate them. So a Velcro is the perfect example or analogy to an intermolecular force, and I'm going to attach a Velcro between these two molecules, and they're now together. But if I add energy, the first thing that is going to be pulled apart is actually the Velcro, or the intermolecular attraction. And so I form individual hydrochloric acid molecules when I have enough energy to separate the intermolecular forces between molecules. So think about it this way. The thread and needle represents intramolecular attractions, and they only happen between atoms. The Velcro is like an intermolecular attraction, and they're much easier to separate, and they combine two different molecules together. When you pull them apart, the first thing that's going to separate is the Velcro, not the thread and needle. I need much more energy to pull apart the hydrogen and the chlorine apart. So here's a learning check. Which of these is an intermolecular attraction? Pause this video and determine whether the A is an intermolecular attraction or it's the B. I hope you mentioned that the intermolecular attraction is B. A, it looks like this is the covalent bond between hydrogen and chlorine. Remember that covalent bonds are an example of intramolecular attractions because it happens between two atoms. But B happens at the molecule level. This is happening between this hydrochloric acid molecule and this other hydrochloric acid molecule. Let's go over these. There are 4 types of intermolecular attractions, so make sure that you write down all of the 4 intermolecular attractions that are shown in this slide. So pause this video, make sure that you have ionic bonds, hydrogen bonds, dipole-dipole attractions, and London dispersion forces, and these are their corresponding definitions on the right. So an ionic bond, it's actually also a type of intermolecular attraction as well. And so I'm going to write ionic bonds as an intermolecular attraction too. And it happens when I have a whole permanent positive charge that is attracted to a whole permanent negative charge. So this sodium is it's positive and this chlorine is a negative ion. This attraction not only happens between these 2 molecules, but it also happens with other sodium chloride molecules as well. Hydrogen bond, that's an extreme partial permanent positive charge, is attracted to another extreme partial permanent negative charge. A dipole-dipole attraction is a partial permanent positive charge and is attracted to a partial permanent negative charge. And London dispersion forces is a temporary partial positive charge is attracted to a temporary partial negative charge. I do want to warn you that this definition of this term, London dispersion force, has multiple names, and I hate it. But I like to call them London dispersion forces, but you'll sometimes occasionally hear just known as dispersion forces. LDFs is another type of another term that we use to describe the same thing, and it's also known as van der Waals forces. So has a lot of names, but it just represents the same thing. The first intermolecular force of attraction that we will be talking about first is a dipole-dipole attraction. So this, make sure that you have all of these 3 bullet points written down, pause it, and replay it or play once you're ready to listen to what this attraction is. This attraction happens between molecules having dipole moments for each other. So that means that this only exists in polar molecules. So this dipole-dipole attraction only exists in polar molecules. So that's why I bolded polar, so that you know that polar molecules experience this type of attraction. Molecules orient themselves to minimize repulsion and maximize attractions. So let's look at this image, which is also a good idea for you to draw. But I have the hydrochloric acid example again. Hydrochloric acid is a polar molecule. The hydrogen, which is the least electronegative, gets the partial positive. The chlorine, which is the most electronegative, gets the partial negative. This partial negative is attracted to this partial positive of another molecule. And this attraction between molecules and charges, that is known as my dipole-dipole attraction. So that's basically what a dipole-dipole attraction is. It's the attraction between a partial negative of one molecule attracted to another partial positive of a different molecule. Hydrogen bonding. This is actually a very important type of intermolecular attraction because there would be no life if it weren't for this type of attraction. So it's a strong dipole-dipole attraction due to large electronegativity difference. So it actually falls under the dipole-dipole category, but I had to separate it and make it its own type of intermolecular attraction because it's just so important and it's a little bit different than just a simple dipole-dipole attraction. And this occurs specifically between a hydrogen atom bonded to either an O, N, or F, oxygen, nitrogen, or fluorine. The partial positive end of the hydrogen is attracted to the partial negative of an oxygen, nitrogen, or fluorine of another molecule. A hydrogen bond is always depicted in dashes, where the partial negative is attracted to a partial positive. And it's actually a very strong force, and it requires a considerable amount of energy to break these hydrogen bonds. So this image and this bottom image, they're super important for you to have written down or drawn, because if you're a visual learner, then it's just easier for you to depict or imagine a hydrogen bond. So remember the requirements of a hydrogen bond. It occurs specifically between a hydrogen that is bonded to another oxygen. This bond, this OH bond, that's a polar covalent bond. So I'm going to have a partial negative on the oxygen and a partial positive on the hydrogen. This partial positive hydrogen is attracted to a partial negative charge, either oxygen, nitrogen, or fluorine of another molecule. Okay, so I depict hydrogen bonds with dashed lines, and it's similar to dipole-dipole attractions, but it occurs specifically between a hydrogen, oxygen, nitrogen, or fluorine of another molecule. So take a look at this image at the bottom. Notice how these hydrogens, they're attached or they're bonded to an oxygen, nitrogen, or fluorine. The only way that this hydrogen has a hydrogen bond with another molecule is if that molecule has a partial negative on a fluorine, oxygen, or nitrogen. So this is the biggest requirement for a hydrogen bond. I'm going to show you an animation of hydrogen bond between waters. So water is a perfect example of hydrogen bonding, and water attributes its main and important characteristics to hydrogen bonding. Without hydrogen bonding, then water wouldn't have its important characteristics that are so vital to us. So hydrogen bonding is the reason why water has a huge melting point and boiling point. So it requires a lot of energy to bring a pot of water to boil. It's also the reason why ions like table salt are able to dissolve in water. So water is known as the universal solvent, and it's specifically attributed to hydrogen bonds. Water also, it's able to, since it requires a lot of energy to evaporate or to boil, then that energy helps, or that energy that it takes away is actually also helpful with perspiration. So the reason why sweating is so important for us is it's because it cools us down. So our body gets really hot, then our body naturally reacts by making us sweat. So that sweat is mainly water. Water requires a lot of energy for it to separate these attractions, and so whenever you evaporate some water, it takes some energy with it. So that's why when you wash something with water and you let it evaporate, it has a very cool or cold sensation, but that's because the water takes a lot of that energy when it evaporates into the environment. So here I have the animation between water molecules, and notice that these water molecules orient themselves in such a way where the partial negative on the oxygen is attracted to the partial positive of the hydrogen. Okay, because this maximizes the amount of attractions and minimizes the amount of repulsion. So here's a learning check, and I'm going to give you 4 types of molecules. And I want you to keep in mind that a hydrogen bond is a type of strong dipole-dipole attraction due to large electronegativity differences, and it only happens when H that is bonded to either an F, O, or N is attracted to a pair of electrons on an F, O, or N of another molecule. So I will be giving you 5 examples actually. So If you want to tackle this on yourself, I have these two molecules, but I have 5 examples, and you're going to have to determine which of these examples is a type of hydrogen bonding. So if you want to tackle this on your own, give it a try. Alright, hopefully you were able to give it a try, but I will be going over this with you. So let's look at this first example. I have this NH3 and this H2O. So this is ammonia and water. Will there be a hydrogen bond that occurs between these 2 molecules? Well, let's actually determine whether these molecules are polar or not. So I see HO, that is a polar covalent bond, and I know that water right away is a type of polar molecule. This NH3 is also a polar molecule. The biggest key to determining whether a molecule is polar or not is if they have lone pairs. So both of these have lone pairs, therefore they're most likely going to be polar. Remember that the atom that is most electronegative gets the partial negative. So this nitrogen in this molecule gets the partial negative. This in this case for water, the partial positive is on the H. So this H is bonded to another O, and it's going to be attracted to another nitrogen. So this is a perfect example of where hydrogen bonding occurs, because this H, which is attached to an O, is attracted to another N. Let's look at this example. Let's see. Will this molecule be able to have some hydrogen bonding? Well, I think I made a mistake in this one because I did not see this part. But this hydrogen is attached to an O, so this hydrogen will be partially positive and this oxygen will be partially negative. And then I have another O. So actually there will be a hydrogen bond occurring here. So instead of orienting it in this manner, it's actually going to look like this. So this is actually the same molecule but just flipped, and therefore this will be a perfect example of hydrogen bonding. Not this orientation, because this hydrogen will not have a hydrogen bond with this oxygen, because notice what this hydrogen is bonded to. It's bonded to C. And this is also a non-polar covalent bond. Alright, let's look at this other molecule, or other example. I have 2 molecules. Notice that this molecule, I think it's formaldehyde. This oxygen and this carbon, they form a bond which is polar, and this oxygen will get a partial negative, but right away I see a CH bond in this other molecule. This CH bond is non-polar, so that means this hydrogen and this oxygen will not be attracted to one another, because the hydrogen has to be specifically bonded to either N, O, or F. So this will not be an example of hydrogen bonding. Let's look at this last example and why hydrogen bonding is so important to us. So back in biology, when you were learning this with Miss Garza, this is how genes are able to stick together. So let's look at this nitrogen and this hydrogen. Well, the only way that this is a hydrogen bond is if this H is bonded to an NO or F, and it's attracted to an NO or F of another molecule. In this case, yes, this is a hydrogen bond. If I do the same process for all of these types of attractions, then yes, all of these will be considered hydrogen bonding. So that's why hydrogen bonding is so important to us. They actually hold our genes together. The last type of intermolecular attraction is known as London dispersion forces. And so London dispersion forces it's actually a big name, so you might hear me say multiple times LDFs, and that just means London dispersion forces. So pause this video, make sure that you write all of these bullet points down, because this is the definition of a London dispersion force. Remember that I said that London's dispersion forces also has a different name. So this is also known as van der Waals forces. LDFs occur because of momentary electron imbalances, which can induce the same adjacent molecules. So electrons, as you know, they're not orbiting around the atom. They have an electron cloud, and they're able to move around close to the atom in whatever direction that they desire. So they're actually very unpredictable to locate sometimes. Sometimes there's a probability that all of the electrons will be located on one side of the atom and then leaving a positive charge on the side where there's no electrons. So this is actually the basis of what a London dispersion force is. They're relatively weak forces that exist in anything with electrons. Any molecule has electrons. So all molecules have some sort of London dispersion forces. They predominate in nonpolar molecules and noble gas atoms. And so LDFs also exist in compounds that have dipole-dipole or hydrogen bonding, and are even more important forces in large molecules of these types. So make sure that you have all of these written down, and then I'm going to go in detail what London dispersion forces are. And so we're going to determine molecules with stronger London dispersion forces. So I have a molecule with strong London dispersion forces when I have a substance with more electrons. So if I have a substance with more electrons, that simply means that I have more atoms and more bonds. If there's a tie, then the substance with electrons on the highest energy levels, that means that it's more polarizable. So the biggest takeaway from London dispersion forces are greater when I have a bigger molecule because I have more electrons. And so electrons, they don't like to stay in one place, they like to move around. And sometimes the electrons are going to concentrate in one region, making that region very negative, while leaving the region that they were in a positive region. So with that being said, substances with more electrons have stronger London dispersion forces. Which of these three examples will have a higher London dispersion force? So take a moment, determine which of these three examples will have a stronger LDF. I hope you said chlorine. So this Cl2 actually weighs more, has more electrons than either nitrogen or hydrogen. Hydrogen doesn't have many electrons. Nitrogen has more electrons than hydrogen, but chlorine just simply has more electrons. So the more electrons a molecule has, the stronger the London dispersion forces are. Another rule of thumb for London dispersion forces: the bigger the molecule, the more atoms I have, then the greater London dispersion forces that I have as well. These are the relative strengths of intermolecular forces. And compounds that are ionic, those are the highest types of intermolecular forces. That's why it takes a lot of energy to melt some table salt. So remember that it's more than 1,000 degrees to melt some table salt because it's an ionic compound. So those have the strongest intermolecular forces present. Ionic compounds also have LDFs because they have electrons. The second strongest type of intermolecular force, they're covalent compounds that contain hydrogen bonds like water. And that's because hydrogen bonds, it occurs between hydrogen and another NO or F, and the electronegativity difference is just very big, and the attraction is also very strong between hydrogen bonds. Polar covalent compounds, those are going to have dipole attractions. So this only occurs between polar compounds, and polar compounds will also have LDFs. Then I have compounds that are non-polar, and the only type of intermolecular forces present is LDFs. So notice that every single type of compound, either ionic or nonpolar covalent, LDFs is present, and that's because anything with electrons will experience some London dispersion forces. So these are also the relative order of boiling and melting point, where ionic compounds have the greatest magnitude of boiling and melting points, while nonpolar covalent compounds of the same weight, they will have the lowest boiling point. So this is actually the last slide, and I'm gonna end it with a learning check. So this question's asking, which intermolecular attractions exists in these molecules? And so I have these molecules of the same kind, and I'm gonna have to determine whether any of these are present. So if you want to give it a try, first pause this video and give it a go. I hope you were able to at least attempt it, but let's just focus on one example at a time. So I have this FH molecule. This is actually hydrofluoric acid, and hydrofluoric acid molecule is a polar molecule. The reason why, it's because this bond is polar covalent. That means that I'm gonna have a dipole-dipole attraction. But remember, and the first thing that I should have mentioned, anything that has electrons will have dispersion forces, or London dispersion forces. But because this molecule is polar, where the fluorine's going to have a partial negative and the hydrogen's going to have a partial positive, I'm going to have a dipole-dipole attraction between this partial positive and this partial negative. Oops. Never mind. It's going to have a hydrogen bond, because it's not a dipole-dipole attraction. Instead, it's a hydrogen bond, because this hydrogen is bonded to this fluorine, and this hydrogen partial positive is attracted to another fluorine of another molecule. So although this is a dipole-dipole attraction as well, specifically it's a hydrogen bonding attraction. Okay, so that's why I did not check it off, because the hydrogen bond supersedes that definition. Let's take a look at this other example. First thing first, let's just determine whether these molecules have electrons. Anything with an atom has electrons, so that's going to have dispersion forces right away. The second thing that we need to determine whether these molecules are polar or not. So CHCl3, this bond between CH, that's non-polar, but this chlorine and carbon bond, they are polar. This is an asymmetrical looking compound or molecule. Therefore, I am going to have polar molecules, where the carbon's going to get a partial positive because it's the least electronegative, and chlorine's going to be the partial negative. It's going to get that partial negative charge. This partial positive is going to be attracted to this partial negative. And remember that polar molecules experience dipole-dipole attractions. So that's another check. Do I have any hydrogen bonding? Well, let's determine whether that is the case. Well, I do have a hydrogen atom, but notice that this hydrogen atom is bonded to a C. In a hydrogen bond, that hydrogen has to be bonded to either a nitrogen, oxygen, or fluorine. Therefore, I will not have hydrogen bonding in this case. Let's look at the third example, and I already gave it to you, but it should already be known that any molecule with electrons has dispersion forces. So that's given right off the bat. But is this molecule or this molecule polar? Well, let's determine the type of bonds that exist in this molecule. So I have a C-C bond. Remember, any atom bonded to itself, like C and C, that's an obvious nonpolar covalent bond. This CH bond, which dominates this entire molecule, is also a nonpolar covalent bond. So this CH bond, I told you that this has to be remembered as a nonpolar bond. because this molecule itself doesn't have any polar covalent bonds, then the molecule itself is nonpolar. Therefore, I cannot have any hydrogen bonds or any dipole-dipole attractions. Moving on to the next example. The next example, obviously right off the bat, you should know that anything with atoms or electrons has dispersion forces. The second thing that we need to determine whether these molecules are polar or not. So right off the bat, I see some non-polar covalent bonds, but I do see some polar bonds, and it's actually very asymmetrical looking type of compound. If you see asymmetry, then that's a perfect cue for a polar molecule. This molecule actually has a lot of partial positives and negatives. Oxygen and hydrogen. Let's just focus at one bond at a time. This oxygen and this hydrogen form a polar bond. The partial negative is always given to the most electronegative atom. So oxygen is the most electronegative atom between these two. Therefore, hydrogen will be partial positive. Let's look at this bond, the CO bond. The C and this O, well, this O is more negative, more electronegative than this carbon. Therefore, the oxygen in this bond will also be a partial negative, and this carbon will be assigned a partial positive sign. Since they're basically the same molecule, it's gonna have the same partial positives and negatives. Let's look for hydrogen bonds first. So let's look for hydrogen that's bonded to another oxygen, nitrogen or fluorine. So I actually see this hydrogen that is bonded to another oxygen. So this has the potential of doing a hydrogen bond with another oxygen or fluorine. So I can actually have a hydrogen bond between this hydrogen and this partial negative oxygen. So right off the bat, I do have a hydrogen bond, but I also see some other type of attraction, and this one was actually tricky. But notice that this oxygen is partially negative. Could there be an attraction between this partial positive carbon? Yes, there can be. So this oxygen and this carbon, they form a dipole-dipole attraction. This other question is asking, rank all of the molecules in terms of melting points from number 1 having the highest melting point from number 4 to being the lowest. So before you actually try attempting this, the molecule with the least amount of forces will be the one with the lowest melting point, and the molecules with the highest amount of forces or attractions, that's going to be your molecule with the highest melting point. So with that being said, pause this video and rank these molecules based on melting points. So let's just focus on the molecules with the most types of intermolecular forces, and this last example has all 3 types of intermolecular forces, and therefore this one is actually going to be the molecule with the substance with the highest melting point, and that's because I have all the different types of intermolecular forces present in this molecule. Now I have to determine which one comes in second place, and so I know that this one is actually going to be last place because this one only has dispersion forces, and dispersion forces they have the weakest intermolecular forces of attractions relative to other types of attractions. So it actually boils down to these 2 examples, but one of these, either hydrogen bonding or dipole-dipole attractions, is stronger than the other one. Remember, hydrogen bonds, they're very strong intermolecular forces of attraction. So therefore, because this one lacks hydrogen bonding, but this one does have hydrogen bonding, this would come in second place. Now it boils down to these 2 molecules. We're going to compare them. This one has more intermolecular forces of attraction present, so this comes in third, and because this one only has dispersion forces present, it comes in last. So This one would have the highest melting point, while this molecule or this substance has the lowest melting point. So that is it, guys. I hope that I tried making this as clear as possible, but I will be posting other resources, other explanations from other people, so that you can wrap your head around intermolecular forces. Again, keep in mind, this concept is heavily tested in organic chemistry, and you will also see it in general chemistry when you go to college, and you'll be taking those courses if you're interested in the STEM field. So thank you so much for tuning in. Make sure that you do that survey and that you also finish your assignments. Keep turning them in, and have a good one, guys.